motion of a charged particle in a magnetic field. When a charged particle of charge q moving with a velocity v enters in a magnetic field of strength b vector, then the force on the charged particle is given by this equation. Fm is equal q v cross b vector. The magnitude of the force is given q vb sine of theta. Theta is the angle between v vector and b vector. This is the relation, and if we observe that if theta is equal to 90 degree, then this force will be maximum q vb, because sine 90 degree is equal to 1, it is maximum. Okay. So when a charged particle moves with a velocity v in a magnetic field of strength b along the perpendicular direction to the magnetic field, then maximum force will be experienced by the charged particle, which is given by this simple formula. Now, if the charged particle, suppose the charged particle enters in a magnetic field which is perpendicular to this blackboard, and the v vector, it is velocity of charged particle, enters in this magnetic field perpendicularly. So v vector, magnetic lines of force, is directed perpendicular to this blackboard. The dotted dots are given to represent the magnetic lines of force. Then what happens? The force will be, according to Fleming's left-hand rule, the force will be perpendicular direction to this magnetic field as well as the velocity of the charged particle. So its direction will change and it will follow a circular path. Okay, it will follow a circular path because at each and every point the force will be perpendicular to the direction of v. So when force acts on the charged particle, definitely it will be deflected sideways. So the direction of velocity changes. It means that the magnitude of velocity remains constant, only its direction changes. That is speed, which is the magnitude. Speed remains constant, direction changes, and it follows a circular path. Suppose the radius of the circular path is r. So according to centripetal force relation, which is Fc is equal to mv square by r, we obtain a balanced condition that Fc should be equal to Fm. This is the magnetic force. So QVB will be mv square by r. From this relation, we can have the value of the radius as mv, vv will be cancelled by qb. So this is the radius of the circular path followed by the charged particle. Now, how we'll find the frequency of the charged particle? Because it will follow a circular path. It completes a semicircle up to this. As you know that the angular velocity omega is given by, v is equal to r omega. If v is the linear velocity, omega is the angular velocity, then there is a relation, v is equal to r omega. So omega is equal to v by r. So omega is equal to v by r. From this relation, you can find the frequency also. So here it is r, it is v. So if you divide v by r, so what you will get? This expression gives v by r will be qv by m, right? So v divided by r, qv will be the numerator and m will be denominator here. So omega is equal qv by m. This is the relation of angular velocity of the charged particle. Now, as you know that omega is equal twice pi f or nu. That is frequency, or you can, in some textbook you will find it n, or in some textbook you will find it nu. Twice pi nu, that is in accordance with the angular velocity formula. Twice pi by t. T is the time period of oscillation. Twice pi is the total angle. So 1 by t is equal nu, as you know. So here nu is equal omega by twice pi. So if you put the value of omega, you will get a frequency qv twice pi m. This is the frequency, and with this principle, an instrument called cyclotron is also constructed, and this frequency is called cyclotron frequency. So with the help of this equation, we can find out the frequency of this charged particle, and with the help of this equation, we can find out the radius of the circle followed by the charged particle. So these are the two relations. So from this principle, cyclotron is constructed. So how cyclotron is constructed? Cyclotron is an instrument that is application part when charged particle moves in a magnetic field. And what are the applications? The important application is cyclotron. And it was constructed by Ampere in 1820. Cyclotron. So, what is cyclotron? This instrument, that is this mechanical method, is used to increase the energy of charged particles. It may be electron, it may be ion also. So one of the application is to increase acceleration. Acceleration to increase acceleration of charged particles. It may be ion or it may be another charged particle, to thereby to increase energy of ion beam or electron beam, etc. So mainly there are two uses of cyclotron. One is to increase the acceleration and another is to increase its energy. As well as when acceleration increases, definitely its energy will also increase. So kinetic energy will increase. So how it is constructed? It is included in your syllabus. Construction, the construction part. In cyclotron, there are two Ds. Ds means uh, the shape is similar to the letter D. Two Ds are there. So inside the D, it is hollow. An oscillator is used to oscillate to supply voltage, alternating voltage. Two Ds are there. So electron beam enters here, or ion beam enters from at the center, and it circulates, and finally its energy is increased. This is the way through which the finally leaves the system. So how it works? Suppose this is D1 and this is D2. Okay. And two Ds, metallic Ds, shapes are like the letter D. They are hollow inside, metallic shape that is made up of some metals, and at the center electron or ion beam is allowed to enter within the D, and one magnetic field is applied. Suppose the magnetic field is perpendicular to this blackboard, that is the lines of force perpendicular to this blackboard. So one magnetic field is applied. As soon as magnetic field is applied, the electron follows a circle. So how the radius of the circle increases? Okay. How the radius of the circle increases? You see, this is a simple construction of cyclotron. To increase its acceleration or to increase its kinetic energy, this oscillator is applied. The cyclotron frequency and the oscillator frequency should be in phase, so that when suppose in the first cycle, as soon as the electron beam or ion beam, if it is positive ion, if positive ion leaves first D1 at this point, and it D2 potential decreases due to the time period of this oscillator. That is, its voltage become lower than this. As soon as the voltage potential of D2 becomes lower than D1, it attracts electron beam, a positive ion beam. So it will be accelerated within from this D to second D, from D1 to D2. Again, when it enters D2, when the beam enters D2 and it follows, it completes one circle, one semicircle, and arrives at this point, at this point, then again each potential becomes lower than D2. The potential of D1 becomes lower than D2. As soon as its potential becomes lower than D2, it will attract the positive ion beam towards this direction with a force, then it will be again accelerated. In this way, its speed or its acceleration increases. Suppose again it moves to this point, okay, it comes to here, its radius increases, and at this point again it is attracted by other D's because its potential becomes lower than this, so it will be again accelerated towards this. So its radius again increases. Okay. So in this way, finally, the beam gets high energy and it leaves the system with a high speed or high acceleration. That is increased acceleration, the beam leaves the system. So it is the cyclotron. It is used in many purposes. So when high energy beam is required, this instrument is used. In many cases, high energy beam is required. That is, from this relation we get that R is directly proportional to V. That means when M, Q, and B, mass, charge, and applied magnetic field remains constant, the radius is directly proportional to V. When V increases, R increases. So within these two D's, the beam is accelerated. If it is positive ion beam, suppose silver ion beam, then it will be attracted by this beam due to the setting of the oscillator. This D1 will have lower potential than this. As soon as it becomes lower potential, it will attract the beam towards this direction. It means that acceleration of the beam will increase within this region. Again, it reaches at this point. Immediately, D2 potential will decrease because the applied voltage in the oscillator is alternating in nature. Its time period is set in such a way that when the beam reaches at this point, it will be directed towards D2 with an attraction because its potential will decrease. So its speed will increase. Speed means the magnitude of velocity. So velocity increases, radius will increase, right? So radius will increase, it will follow another circle. In the same way, it will follow some higher circles, and finally, it will be too much accelerated, and accelerated beam will leave in this way. So in this simple way, the acceleration of beam can be increased. So another application is mass spectrometer. In the mass spectrometer, uh, let us consider two regions. One region S1, so another region S2, where a beam, electron beam or charge particle beam is allowed to enter in a chamber, suppose S1, having both electric field as well as magnetic field. Suppose this is electric field and the magnetic field is also applied. This region consists of both electric field as well as magnetic field. Okay, and electron beam is allowed to pass through this region, and this magnetic field has the value B dash, suppose, and this electric field has value E. Okay, only value is shown. So within the chamber S1, here there are two fields. One is electric field, another is magnetic field. They are so adjusted that both the field applies equal and opposite force on this beam. When equal and opposite force is applied by these two fields, then it will move undeviated in a straight line. So from that, we can have velocity selector, as when this condition is applied here, then the force due to electric field QE is equal to the force due to magnetic field QVB. It is QVB is the maximum force because the velocity of the charge particle is perpendicular to the magnetic field. So it is B dash. From here, you will get the value of V as E by B dash. So this is the velocity selector. The velocity is selected in such a way this ratio is maintained. So with that velocity, the charge particles enters another region S2, where again single magnetic field is applied, and it will follow a circular path and strikes a photographic plate. Here P is the photographic plate. When beam of charged particles strikes photographic plate, it produces an effect. That effect can be recorded. Where it strikes, there will be some mark. So the measuring this distance, the radius of the circle can be easily calculated. So in this region, if you find the force, that is the magnetic force will be Q V B, because the magnetic field is here, applied here is B. There are two magnetic fields. One is B dash, the other is B. So at this position, since the circle follows a circular path, then it will be equal to the centripetal force mv square by r. So from this you will get q by m as divided by m. V will be there. So 1v b r. So if you put the value of v from this equation, what you will get? E B B dash 1 by R. So the value of R is obtained from the photographic plate measuring this distance. It will be twice R. So R is obtained. The value of E is obtained. The value of B and B dash are also known because applied fields are known. All are known value. By putting all these values, so anyone can calculate Q by M. So the ratio of charge to mass is calculated with the help of this instrument. This is called mass spectrometer. Okay. So this is another important application of this uh, topic, that is motion of charged particle within a magnetic field. So another point is that the magnetic field applied here is uniform. B and B dash both are uniform. So strength of magnetic field is uniform at each and every point. So this is another important relation from which the ratio of Q by M, that is charge to mass, is calculated.